You have so much fun. Okay, so we are going to look at differentials today. Try to keep up. We got f of x, and this spot right here, we will call this a value of x at which we will, whoop, I'm going to move that back. And I'm going to draw the linearization. Draw that in red. Okay, so differentials are useful just like linear approximation. Differentials is kind of a basic introduction to what you would see with differential equations. Uh, I guess kind of we're going to look at differential equations later on, so you'll see this notation to follow. This is the line L, and so it's the linearization, and that's f of x. Now, differentials is different than linearization. Linearization allowed us to approximate the function at a given value. Differentials allow us to approximate the difference. I will show you what I mean. The drawing is very important. You have to do it on your assignment. I'm going to move over a certain amount, and we call that amount delta x. And then I will move up a certain amount, and we call that delta y. So a capital letter for delta in Greek is a triangle. It means change, the change in x, change in y. What's another word for change in x over, or change in y over change in x? Slope. Yeah, so the average rate of change of the function between these two values is the slope, okay? But within calculus, we are not just using delta y over delta x. We've been doing that forever. That's slope. That's algebra 1 stuff. What we are looking at is dy over dx. That means, in this case, delta x is the same as dx. The change in x here is the same. But when we say dy, we're referring to the derivative. So the change in the derivative, in this case, the derivative is the line as it shows the instantaneous rate of change of the function at x. And so dy is the green. It's the distance from the change in x to the linearization, the derivative. Yep, exactly. Delta y is simply the change in the function. So it goes to the function, whereas dy goes all the way up to the linearization. Okay? So what does this mean? Let's just answer a couple questions here. True or false, dx is the same as delta x. True. Our change in x will be the same. True or false, dy is the same as delta y. False. The smaller delta x is, the closer dy will be to delta y. So therefore, it is true. Thank you for affirming. So you're absolutely right. And so as we move it together, that will approximate. So the question is, why would differential of a function be useful? It allows us to use dy to approximate delta y in small intervals. So dy is a good approximation of delta y in close proximity. Okay. We're going to do a number of different examples that kind of help you get a hang of what this is. But first of all, we're going to write an equation for a differential. We're going to use dy over dx is equal to f prime of x. And so if I multiply both sides by dx, I get dy is equal to f prime of x dx. And so if we want to approximate dy, that's all we have to do. That's an easy way to come up with dy. And if it's an approximation for delta y, that's a real easy way to come up with delta y. So we're going to use that formula. It says find the differential dy and evaluate dy for the given values of x and dx. So dy is equal to f prime of x dx. So dy is, what is the derivative of my function? The function is 3x minus 1 over x. What's the derivative of 3x? 3. And then 1 over x is x to the negative 1. What's the derivative of x to the negative 1? Negative 1 over x squared, because you have a minus here, is going to be plus 1 over x squared. Very good. Everybody okay with my derivative? Times dx. So this is the formula that we use, f prime of x times dx. Now, in order to estimate dy, in order to calculate dy, we simply plug in our x value and we plug in our dx. So dy is equal to 3 plus, what is 1 over x squared going to be? 1/4 times dx, which is 0.5 or 1/2. So dy is equal to 3 plus 1/4, that would be 12/4, plus 1/4 is 13/4, times 1/2, which is 13/8. Did we just find dy or delta y? Dy. That is a very close approximation to delta y. Now, you don't know why it would be interesting to use delta y right now, but we're going to get to a couple examples right at the end that show you why it would be interesting to use. Let's do it again. We have, again, dy is equal to f prime of x dx. In order to take the derivative of that, what do I have to use? Quotient rule. However, it would be better for us to use the chain rule because we write to the negative 1 power. So that will be nicer for us. So the inside is x plus 1. The outside is 3u to the negative 1. What is the derivative of 3u to the negative 1? Negative 3 over u squared, and derivative of x plus 1? 1. So we get dy is equal to negative 3 over the quantity x plus 1 squared times dx. So what we have found right now is the differential. This is the differential. We're going to use the differential to approximate or to calculate dy, which approximates delta y. So what do I plug in for x? 1. 1 plus 1 is squared. So negative 3 over 4 times, what's dx? 1 over 100. So we get negative 3 over 400. So again, our goal is to come up with a differential as well as evaluate dy. Got it? Not too bad, huh? But it's different. And that's why, like I said, open note test for this short little bit. Just because it's information we're going to come back to, but you want to see it right now so you know what we're doing. All right, example 4. Compute delta y and dy for the given values of x and dx equals delta x. Sketch a diagram for showing the line segments with lengths dx, dy, and delta y. We'll do it when we get back from lunch, have some brain food, come back ready to go. All right. Okay, hope you had a good lunch. Compute delta y and dy for the given values of x and dx equals delta x. Sketch a diagram showing line segments with lengths dx, dy, and delta y. You tell me, what does the graph of x to the third plus 1 look like? Yep, shifted up 1 unit. Let's draw it. I know this isn't a great graph of x to the third plus 1, but I got to try to make it work for the drawing. So that's kind of what I'm doing. So where do we want to evaluate it? X equals 1. we're just gonna get a few flakes. No, in fact, the temperature is supposed to stay warm where it's right around 32 degrees. Everything's gonna melt. Don't worry about snow. All right, so I'm gonna draw my line tangent, and you're not gonna like how I draw this, but it's just what I kind of have to do. What is delta x? What's my change? 0.2. So that would take me from 1 to 1.2. So I'm fully aware that that's not to scale, right? But just trying to make the drawing so that we can see it. So this is dx is delta x, which is 0.2. If delta x is 0.2, then I have to go 0.2 units over from 1. And 1 plus 0.2 is 1.2. So what do you want to draw now, dy or delta y? Okay, we'll go delta y. You tell me. Does delta y go to the black curve or the red line? Which is it? Why does it go to the curve? Because delta y represents the change in the function, not the derivative. Okay, so dy is going to be that. It's going to be the vertical change in the linearization. Okay, so delta y you draw to the function, dy you draw to the line. Look at what we did up above. Okay, delta y is to the function, dy is to the line. Now some people say, well, dy's could be the longer one. Not necessarily. This is an overestimate here. This is an underestimate here, and so we'll talk about that. So we sketched it. Now we want to compute delta y and dy. I'll start by doing delta y. Delta y's can be the change in the y values. y2 minus y1. How do I calculate the second y value? What do I plug in? 1.2. So 1.2 to the third plus 1 minus, how do I calculate y1? Plug in 1. So that'll be 1 to the third plus 1. So I plug in the x2 value to come up with y2. Okay, so we got 1.2 to the third plus 1. Now I get 2.728 minus, that's going to be 2. And so we get 0.728. So that's the length of the green segment there. So now I'll calculate dy. Remember, dy is an approximation for delta y. In order to calculate dy, I use f prime of x times dx. That's a differential. So dy is equal to, what's f prime of x? 3x squared dx. What do I plug in for x? 1. So I get 3 times, what's dx? 0.2. What's 3 times 0.2? 0.6. So you can see I come up with 0.6 for the blue segment. So we get 0.6 and 0.78. So was dy an underestimation or an overestimation? It's an underestimation, and you can decide whether that's close enough or not. But the fact is I need to know the height of the function at 1.2. So I plug in 1.2 and I cube it and I add 1. So that's my second y value. Right there. To get 1, to get y sub 1, I plug in 1. 1 to the third is 1 plus 1 is 2. The height of the function at 1 is 2. The height of the function 1.2 is 2.728. Yes? All right. All right, flip it over. Let's do another one. What does that graph look like? Something like that, right? What's the x value that we're focusing on? 6. I'm going to draw the linearization. What would you like to draw first? Would you like to draw, well, let's draw delta x dx. Okay, so we're going to move from 6 over to what? 6.1. Now, again, I know you might not like this, but I want to have room to draw. So that's 6.1. I know it's not really to scale. We got to make the drawing fit, okay? So that's delta x is the same thing as dx, and that's 0.1 in this situation. So we moved over 0.1. So I'm going to draw dy. Does dy go to the red or to the black? Dy. What do you guys think? You got one. Red, black, black, red. Goes to red. Dy is the change from the linearization, change from the derivative. Delta y is the blue. So let's calculate delta y. How do you calculate delta y? Y sub 2 minus y sub 1. How do I get my second y value? Uh, 6.1 minus 2 is 4.1. So we got square root of 4.1 minus square root of 4. And I get 0.0248. No, that's y sub 2 minus y sub 1. You've got to plug it in for x. 6.1 minus 2 is 4.1. 6 minus 2 is 4. Because I'm going to plug in 6. And 6 minus 2 is 4. Yes. I plugged in 6.1, I plugged in 6. I plug those in, I get square root of 4.1, square root of 4. Okay, let's calculate dy. What's my formula for dy? F. Good. So I need to come up with f prime of x. How do I find the derivative of that? What do I have to do? Chain rule. So we've got x minus 2, and we got u to the 1/2. What's the derivative of u to the 1/2? 1 over 2 roots of u. What's the derivative of x minus 2? 1. So we get 1 over 2 times the root of x minus 2 times dx. What do I plug in for x? 6. 6 minus 2 is 4. Square root of 4 is 2 times 2 is 4. So we get a fourth. What is dx? Are those close? You can see that if you were to round this to the nearest thousandth, you can put 0.025. So very close. Well, it's all relative, so. Well, I mean, close is relative. I mean, is this close? 0.6, 0.728? Seems to me, but no. No, but you would be asked that possibly on the AP exam. Okay. All right, let's consider this right here. Use differentials. So this would be something that Newton would have done. Okay, so Newton's sitting there. He's got no calculator. How does he come up with the square root of 64.3? He wants a good estimation. And he could come up with a really good estimation. It's not that difficult. And I'm going to show you guys how. Square root of 64.3. I know that the square root of 64 is, try again. I know that the square root of 64 is 8. So I'm going to choose a function, square root of x, and I'm going to choose an x value of the square root of 64. Who can tell me what delta x or dx is going to be in this situation? How far am I moving from the x value of 64? 0.3. So we will come up with a differential to figure out, if we move over 0.3 from 64, how much up should we move from? If I move 0.3 over from 64, how much should I move up from 8, right? So let's say we come up with the differential being, we come up with, say, 0.1. Our answer won't be 0.1, but 8.1, okay? If we come up with 0.25, then our answer would be 8.25. So it'll make sense here in a second when we write it out. We have dy is equal to f prime of x dx. I'm going to use that to approximate square root of 64.3. So dy is equal to, what is the derivative of my function? Square root of x. 1 over 2 roots of x times dx. So dy is equal to, what do I plug in for x? 64. Square root of 64 is 8 times 2 is, so I get 1 over 16 times 3 over 10. I get 3 over 160. So it looks like if I move 3/10 in the x direction, I should move 3/160ths in the y direction. So what we've said is that the square root of 64.3 should be approximately 8 and 3/160ths. I know you're just dying to find out, because I am too. If we take 3 divided by 160, we add 8 to it, we get that. So let's compare that to the square root of 64.3. And Newton would have known that it was an overestimation because he could have graphed it. Right. That's not calculus. We can teach our first graders to type in the calculator, can't we? Question. Newton knew how to graph this function, square root of x, just like we did before, and he chooses an x value of 64. Because he looks at the linearization, he realizes it's an overestimation. But he knew what the square root of x looked like. He just punch in enough values to figure out exactly what it looks like. Square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. Generate, he knew you couldn't plug in negatives because that would be imaginary. So pretty good, pretty good. All right, what's my function here? I want to take 3.01 to the 4th power. I know what 3 to the 4th power is. What's 3 to the 4th? Ooh. 81. Yep, 3 times 3 is 9, times 3 is 27, times 3 more is 81. What's my function? X to the fourth. What is my x value that I'm evaluating in the set? 3. What is my delta x or my dx? 0.01. So we have dy is equal to f prime of x dx. Or dy is equal to, what's f prime of x? 4x to the third times dx. So dy is equal to, you take 3 to the third, which is 27 times 4, 108, times 0.01. And I get 1.08. So is that my answer? If I plug in 3 for x, 3 to the third is 27 times 4 is 108. Times 0.1 is 1.08. That's not my answer. What do I have to do? Not add 3, but add 81. So that would mean that 3.01 to the fourth power is approximately 82.08. What's that? Because we know that 3 to the fourth is 81, right? So if we move over 0.1, 0.01, how much will we move up from 81? So that's how much we move up from 81. And if we calculate that, 3.01 to the fourth power, I get 82.085. And as you can see, I'm pretty close, huh? Not too bad. All right, so the application. This is where this is a great time to make application moving forward, and this is good that we've come out of our related rate section. We're probably going to go over by 1 minute, but that'll be all right. Radius of the circle was measured and found to be 5.4 centimeters with a possible error of at most 0.1 centimeters. So when you're measuring a radius of a circle, do you think it's possible you could be off by 0.1 centimeters? Okay, then the question is, how far off would the area be when you're actually computing it? Is it going to be off by then another 0.1? What type of error will we receive for double? Okay, 0.2. We got to guess there. Let's check. What's our formula for area? Area is equal to pi r squared. What is our radius value at which we're evaluating this? 5.4. No, because it's not a full related rates problem. So our radius is 5.4. Can somebody tell me what dr is? 0.1. The change in the radius is 0.1. Might be positive 0.1, might be negative 0.1. Let us take the derivative of area. What's the derivative of A? A prime equals 2 pi r, r prime. And instead of writing r prime, dr is the same thing as r prime. So A prime is equal to 2 pi. What's my radius? Times dr, 0.1. Type it in. You get 3.39. Now, so that's the error. It's error. It's not double. It's who knows what. It's 3.39. It says what about the relative error? Okay, and what does that mean? What that means is we take the error and we divide it by the calculated area. So I'm going to take 3.39 and divide it by the calculated area. How do I find out the calculated area? Plug in. What do I plug in? Yep, so 5.4 squared. And I multiply that by pi. I get 91.61. So 3.39 divided by 91.61 is going to give me my relative error. So relative means 3.39 is not that much if we're talking about area of 1,000. But if we're talking about area of 6, then 3.39 is a heck of a lot, isn't it? I plugged in 5.4 into my area formula. Let's divide it. 3.39 divided by 91.61, and we get 0.037 or 3.7% is our relative error. So the assignment I'm giving you today is follows exactly like your notes. Please follow on. It's shorter than the assignment I gave last year. You have a work day tomorrow. You have a work day on Thursday. You have a test on Friday. Go Gadget, math.